Hi, thanks for joining us here today. We are Zero Dark 30, and I'm Kyle McWood.
I'm James McInnes.
I'm Matthew Cook.
And we're here today to talk to you about the Aircraft Navigational System, also known as the NAV2K. In this video, we'll be going over the engineering requirements, so the overview of the block diagram, and also some unique design concerns. The NAV2K receives three different signals. The first being the VOR, and the second and third being the ILS system. The VOR signal, combined with the navigational system, create the high waves in the sky. And this is how the pilot travels from one airport to another in the most direct route, safely. The ILS system consists of two separate parts. These are the localizer and glide slope. The localizer controls the horizontal, and the glide slope controls the vertical. And this allows the plane to land safely, even through thick cloud cover. So the localizer and glide slope receive the composite signal from the receiver, and take the composite signals and split them into their 90 and 150 Hertz components. And the interesting challenge this holds is splitting the composite signal into two different signals. This requires extreme, precise filtering. In order to do this, we use tight bandwidth filters. And the problem with this is that those filters use capacitor. And the capacitors can vary plus or minus 20% in overheating and temperature range. And this produces a big problem to the signal that we're trying to create. Also, another tricky engineering requirement we're going to have to fill is that it needs to be within 5% error so that the plane lands directly in the middle. So it can only be 5% off to the left or right.
Right now I'm going to give you a good general overview of the block diagram. Starting with the outside of the unit, we've got two major things coming in through that case that we have right here. You've got your environment, which is going to consist of temperatures that this unit has to survive as according to the FAA, as well as the received RF signal. That RF signal is actually two signals that we're looking for, one of which is 108 megahertz to 117 megahertz. The other one is 329 megahertz to 335 megahertz. Those two sets of frequencies make up the aviation navigation band. Those frequencies go into our receiver. Our receiver takes that, splits them apart, and essentially gives us two video signals, one for the localizer and VOR subsystems, which is chosen depending on frequency, and the glide slope system. That signal goes out of there, those composite signals exit, and depending on which mode we're looking at, which is determined by frequency, it either goes into the ILS converters and gives back deviation information on left, right, and up and down for landing planes, or it goes into the VOR subsystem, which, as Kyle noted, takes care of navigating on the highways in the sky. Those converters, after taking that information and splitting it up into something a bit more readable by a digital microprocessor, go into the microcontroller. The microcontroller uses its code to figure out the deviation information or to give the information necessary to land the plane. The user interface is actually rather simple. It's two alphanumeric HP displays that only show the volume level and the frequencies. Two dual rotary encoders allow easy control of volume and frequency input. Well, at the push of a button, you can swap those two frequencies for whichever one is active. The analog deviation output system is what essentially connects all the converters inside the unit to the outside world. It takes your left, right, and up and down information and converts it into analog movements and DC voltages for outputting to an autopilot, as well as sending off to a head display. The case of the unit is going to be a nice milled aluminum system, which is being provided to us by our sponsor, Val Avionics Limited, and made by my boss, James Harr. power supply is actually a rather simple item, because the power supply consists of nothing more than 3 individual units, 2 5-volt power supplies, essentially taken from linear technologies and dropped into place, as well as a 5-volt to plus and minus 12-volt power supply for dealing with the analog subsystems that require greater precision. Finally, we have the resolver subsystem, which is a fascinating piece of equipment that allows for the conversion of a mechanical position into a 360-degree plane. But as you can see, that is the block diagram. Thank you much. Next up, Matt Cook is going to talk to you about why we decided to go with this particular project instead of any number of other projects that we could have gone with.
Thanks, James. I'm going to take a moment and share with you why we chose this project. We have discovered that there are lots of different products out there, and one reason we chose this, one aspect that we're changing in this product is we are updating the technology and we are downsizing this product to a compact space. As you can see, this unit here is both a nav and a comm, and it's very large. This nav has dual layered switches, old technology, and has the old transformers involved. This is a comm 2000. This nav is much smaller, as you can see, and this is what we're going to be designing. Small aluminum case, as James described earlier, the LED screen. Okay. As we have discovered by researching other designs out there as far as UHF, VHF receivers go, we wanted to make ours unique. So one way we did that was we brought newer technology to the table, and we also made it more compact in order to go into the cockpit of an airplane, which we have also discovered that this space in an airplane is very pricey. Okay, here we got our composite signal entering. We got a 30 Hertz bandpass filter and a 9960 bandpass filter. I'm going to start off with the top half here just because it's the shorter one. We're going to go through the bandpass filter, and then we're going to go through a limiter, allowing us to just have our 30 Hertz variable signal. And that's outputted to the microcontroller. This is a DC rectifier, which allows us to test if the flag needs to be raised. Now, going down here to our other bandpass filter, 9960 Hertz, we're also going to square that one up and go through our phase locked loop. And this part is analogous to the upper one up here. And this phase locked loop allows us to demodulate our 30 Hertz signal from the 9960, our 30 Hertz reference signal. Then we filter it and we limit it, and allow us to also go to the microcontroller. And this is another DC rectifier, which checks to see if no flag needs to be raised. And so these are the two signals that are going out to our microcontroller. Okay, one engineering requirement I'd like to go over is the phase shift. We can only be within 3 degrees error, plus or minus. So in order to overcome that, what we're going to do is be very specific in our part selection, capacitors in particular. In normal capacitors, you can have up to 40% error over temperature. And so in our case, we're going to be choosing ones with a lot, significantly less, obviously less than 2% in our case.
Thank you for joining us today for our video presentation about the Val Nav 2000.
I showed you about the localizer and glide slope and how the pilot can pretty much land without having to see anything.
I showed you the VOR converter board and some interesting aspects that goes along with that board in our system.
Our goal is to make certain that we have all of our schematics, all of the boards done, and sent off to be manufactured. And over winter break, we're going to be beginning our initial testing and validation of the system in total. So that way we can attempt to be finished by December 31st of this year. It'll be a Happy New Year.
Thanks for watching.